Greetings, fellow nerds. In this video, I'll be sharing my lab notes on trying to make potassium permanganate. Potassium permanganate is quite useful as a strong oxidant, and its beautiful purple color also confers extra uses as an indicating titrant for redox titrations. I demonstrate this when I titrate hydrogen peroxide. But it's come to my attention that potassium permanganate is difficult to get for some individuals, and a method for making it would be helpful. I did try to make it over 10 years ago, but I was using a bad technique and I wasn't really putting in any effort. So now it's time to revisit that project. This is not a full procedure video yet, but these notes might be helpful if you're exploring it yourself and want to avoid the mistakes I made. So my first failed idea was to start with 60 grams of manganese chloride and then precipitate out manganese hydroxide by reacting it with a solution of 40 grams of sodium hydroxide in water. The idea was that manganese salts are easy to obtain as fertilizer like manganese sulfate. So maybe starting from there would be a good idea. The manganese hydroxide was then filtered to remove the sodium chloride salt. Once the filtration was done, I transferred the manganese hydroxide to a new beaker. It's turning brown because oxygen in the air oxidizes the pink manganese 2 hydroxide to manganese 3 oxides. Anyway, I then proceed to add the oxidant of 60 grams of potassium chlorate. I was thinking that this should oxidize the manganese 2 ions to manganese 6 oxidation state during the heating step. I made my potassium chlorate from both electrolysis of potassium chloride as well as disproportionation of bleach. I also added 60 grams of potassium hydroxide, which will provide the potassium ions as well as the strongly alkaline conditions needed to stabilize the higher oxidation states of manganese. Looks like I added too much water to my mixture, so to prevent it from boiling over when I put it in the oven, I boiled off some of the water on the hot plate until it became a thick paste. Finally, I transferred it to an iron can since heating a strong base like potassium hydroxide to 300 Celsius would dissolve the glass. I then put the can into a furnace and ramped the temperature up to 300 Celsius. My idea was to react the manganese hydroxide and oxides with the potassium chlorate and potassium hydroxide to produce potassium manganate. Normally in the industry, air is blown into the molten mixture of manganese dioxide and potassium hydroxide to oxidize it. But that's a rather complicated setup, so as amateurs it's more straightforward for us to use potassium chlorate as our oxidant. Anyway, I let that heat for several hours. After it was done, I let it cool and then took it out of the furnace. I dissolved the mixture in water and transferred it out into a beaker. The total volume of water used was about 400 milliliters. I then proceeded to stir it for an hour to break up the chunks. At this point, I filtered it to separate out the potassium manganate from the unreacted manganese oxides. And that is our residue of manganese oxides. The large volume makes me think this did not work out since this is the waste product and not the desired product. Why is so much of it here? Down here in the filtrate is our desired potassium manganate. It has this strong green color which is characteristic of the substance and confirms I successfully produced some. But it's not yet potassium permanganate, so I need to oxidize it 1 electron further. To do that, I constructed a chlorine generator consisting of 50 grams of sodium dichloroisocyanurate in water down here, and 100 milliliters of 30% hydrochloric acid up here in a pressure equalized dripping funnel. The acid was dripped into the sodium dichloroisocyanurate and generated chlorine gas that was injected into the potassium manganate solution. What happens is the chlorine directly oxidizes the potassium manganate into potassium permanganate. You can see the green solution become purple as this happens. Industrially, electrolysis is used to perform the oxidation, but that's slow and I didn't want to deal with the complexities of cell design and electrode selection. Anyway, I let the solution stir for a few hours after all the acid had been added and the chlorine injected. Once that was done, I filtered out the mixture, hoping the potassium permanganate precipitated out. Looking at the filter funnel, something did precipitate. It looks like there is muddy manganese dioxide on top of something crystalline on the bottom. However, potassium permanganate should be black, so I wasn't sure what this stuff was. Maybe it was a trick of the light and I just needed to recrystallize it for purity. So I boiled some hot water and dissolved the product right on the filter funnel and suction filtered it through. Here is the filtrate. It certainly looks like the right color of potassium permanganate, so I chilled the flask for a few hours to crystallize it. Then I filtered it again. Here is a close-up of the product, and this is not good. Potassium permanganate is black, and the crystals are needle-like. Whatever this is, it's not potassium permanganate. The crystals are flakes and bright purple. To further test it, I tried to dissolve some of it in water. If this were potassium permanganate, it should be a deep dark purple with the amount that I put in. This is a failure, as it's much lighter than expected. It looks like something else stained with potassium permanganate, and I strongly suspect this is actually potassium chlorate. So this whole trial was a failure. I didn't isolate potassium permanganate, and whatever I made was too highly contaminated to be of any use. But it isn't a complete failure. I did produce some potassium manganate as evidenced by the green color, and the filtrate after chlorine oxidation is purple, which does indicate I did produce some potassium permanganate. Just the yield was very low. I suspected the problem might be that I did not use high enough temperature when reacting the manganese hydroxides with potassium chlorate. So I performed the whole experiment again, this time using 400 Celsius, and once again filtering, oxidizing with chlorine, and recrystallizing again. But just looking at it right on the filter funnel, I could tell this was still a failure consisting of mostly unreacted potassium chlorate. So clearly the reaction wasn't going far enough. I had lots of unreacted potassium chlorate left over. My next thought was that I was likely wrong to use manganese hydroxide. Manganese hydroxide is in the second oxidation state, and I was hoping that by using lots of potassium chlorate I could go right to the sixth oxidation state and make potassium manganate. But if there is a lot of it left over, then this reaction isn't very high yielding. So for my third run, I went to using manganese dioxide like I should have. My proportions were 43 grams of manganese dioxide I got at a pottery supply store, 25 grams of potassium chlorate, and 60 grams of potassium hydroxide. I mixed them up and heated them in a furnace at 400 Celsius for several hours. Once again, I performed a similar workup of dissolving it in water, generating and injecting chlorine gas. I then filtered to remove any dissolved potassium salts. Next, I boiled some water and dissolved and filtered the residue on the filter funnel to hopefully recover any potassium permanganate. This time, the color looked great and I had high hopes for it working. I chilled the filtrate in ice water for a few hours and then proceeded to filter it. And this looks much better than before. Those crystals are actually black with maybe some yellow tint. This is much closer to what potassium permanganate should look like. I took a few crystals and dissolved them in water, and this dark solution is very promising. Potassium permanganate is extremely strongly colored, so getting this much color from just a few crystals is a strong indication we're on the right track. I let them dry on the filter funnel overnight and then collected them for yield. Total mass obtained was 15.4 grams for a total yield of about 19%. But of course this number is useless if the purity is bad, so I performed a titration on the potassium permanganate to determine the purity, and I found it to be 99% pure to within about 3% error. So we can safely say this was a successful attempt at making potassium permanganate. I'm still improving the method, and I can already see a few procedural changes to increase the yield. But at around 20% yield, this is already good enough for amateur synthesis, as the reagents are not that expensive. It seems the source of failure for me was starting with a manganese 2 hydroxide or oxide and trying to oxidize all the way to manganese 6. It seems this just doesn't happen with high yield. Unfortunately, this closes off a fair number of easy manganese sources like fertilizer manganese sulfate. Conversion of manganese 2 salts into manganese dioxide is a bit more involved, and I was hoping to skip that. Fortunately, manganese dioxide itself is not too difficult to obtain as it's available for pottery purposes. While it can be obtained from batteries, I'm worried about the presence of carbon that would reduce it back down to manganese 2 during the furnace heating step. But those are considerations for future experiments. This method of using pottery-grade manganese dioxide to make potassium permanganate works right now. So I'm going to optimize this a bit more, and I should produce a video soon on making potassium permanganate. Thanks for watching these lab notes. I hope that was interesting. Special thank you to all of my supporters on Patreon for making these science videos possible with their donations and their direction. If you're not currently a patron but would like to support the continued production of science videos like this one, then check out my Patreon page here or in the video description. I really appreciate any and all support.